Hi guys. If you are a 2023 A-level maths student, you would have done your paper 2 exams today. So hopefully that went well. In today's video, we're going to do a paper 3 Edexcel exam. So this is the final question, so the hardest question from if we just scroll up, the 2022 paper 3 stats exam. So if you're an Edexcel student, paper 3 is in two parts. So part 1 is stats. Part 2 is mechanics. We're going to do the last question on the 2022 paper 3 statistics exam for your A-level maths. So it's this question here. So question number 6. So we've got Anna investigating the relationship between exercise and resting heart rate. She's going to take a sample of 19, a random sample of 19 people in her year at school. And she records for each person their resting heart rate, H. So H is the heart rate on the y-axis there, and the number of minutes m, so minutes is on our x-axis, is the amount of time spent exercising each week in minutes. So that's the data we have, and we got this result here on the scatter graph. So we've got to interpret the nature of the relationship between h and m. So this is as we can see from the graph here, we've got a negative correlation, don't we? So I mean, as the minutes of exercise increase, then the resting heart rate seems to decrease. So that's a negative correlation. So with that one, the part A of the question, we just want to say negative correlation. So there's a negative correlation. So negative correlation. Sorry, let me try and write a little bit neater. Negative correlation between the two variables. So between the heart rate, which was h, so between h and m. Okay, so you got that for part A of the question. So now let's go to part B. So Anna codes the data using the formulae below. So x is equal to log base 10 of m, and y is equal to log base 10 of h. So the product moment correlation coefficient between these new variables x and y is given by this here. So it's given by negative 0.897. So we want to test whether or not there is significant evidence of a negative correlation between x and y. So we've got to state our hypotheses clearly, use a 5% significance level test, and we've got to state the critical value that we used. Okay, so for this question here, we're doing a hypothesis test. So doing one of these product moment correlation hypothesis tests. So we always, when we do our hypotheses, these kind of bivariate data tests, so these kind of tests where we're using bivariate data, we're comparing two variables. Our null hypothesis, we've got to state a hypothesis first. So our null hypothesis is always this. So it's always rho. So with this product moment correlation coefficient, remember we use the letter rho, the Greek letter rho, which is basically Greek for r. So rho, this product moment correlation coefficient, is 0. So that's always our null hypothesis with these correlation tests. So that's always our null hypothesis. So we're always, when we do these calculations, we always assume that the null hypothesis is 0. We always assume that the correlation coefficient is 0. So we always assume that there's no correlation. And then our alternative hypothesis, so the thing that we're trying to test, in this case, we're trying to test whether we've got a negative correlation. As we can see from the question there, we're testing whether or not there is a negative correlation between x and y. So that's kind of what we're testing in this calculation here. So we're testing whether there is a negative correlation. So we want our correlation coefficient variables to this rho to be less than 0. So remember, if your correlation coefficient is less than 0, it means you have a negative correlation. So if you've got if you work out your correlation coefficient, you get a number less than 0. It suggests that your two variables in your data have a negative correlation. So we're testing. So when we do the calculation, we initially assume that there's no correlation, but then once we calculate our coefficient, we've then got to we're testing this alternative hypothesis whether it is actually a negative correlation between the two variables. Okay, so yeah, so when we so when we do the calculation, so in A-level maths, you don't need to worry about the formula for calculating this product moment correlation coefficient, but there's a formula you can use which incorporates all the data in your data. And you plug that into a formula and you get a number, which basically tells you the relationship between the x-axis and the y-axis. So they did the calculation for us and they got this number here. So they got negative 0.897. Okay, so we've got a R value. So I know that we've used rho in our hypothesis. So the standard procedure in a hypothesis test is that you use Greek letters in your hypotheses, but once you've collected your data, you use normal Latin letters. So R is basically the number that we got from our data. So the number that we got from our data, the correlation coefficient from our data was negative 0.897. Okay, so negative 0.897. So that was, so when we collected our data, plugged all the data into this special formula, that's the number that they got. So negative 0.897. And again, the key thing is we use Greek letters in the hypotheses because basically these are theoretical correlation coefficients. So we use Greek letters for theoretical numbers that we don't know. But when we collect data and actually use formulas, we use these Latin letters. So for example, when you do a normal distribution hypothesis test, you use mu, don't you? So you use mu in your hypotheses, the Greek letter mu. That's your theoretical mean. But your actual mean, you normally call x bar. So normally in a mean calculation, we call x bar mean. So it's the same kind of thing. It's just standard procedure in how in statistics to use this kind of notation. But let's not worry about that. I'll just rub this out here to get more room. Anyway, yeah. So we've got this. So we collected the data, plugged the numbers in the formula, and the examiner's telling us that this is the number we get. So now we've got to do our hypothesis test. And we're doing a 5% significance level hypothesis test. So the first thing to be aware of is that this is a one-tail test. So if we've got a strict inequality sign in our alternative hypothesis, it's a one-tail test. So this is a one-tailed test. If it was a not equal to sign, that would be a two-tail test. But this is a one-tail test because essentially we're only focusing on one end of the spectrum. So if we think about, I mean, I'll draw a number line out in a minute. So again, I'll just write here, this is a one-tailed test. If we think about our correlation coefficient, so this is like a number line of R values. So the maximum possible R value is 1. Again, hopefully you've seen this in class, but 1 is your maximum possible correlation coefficient number. -1 is your minimum, and 0 is in the middle there. So 0 means no correlation. 1 is a perfect positive correlation, and -1 is a perfect negative correlation. So the idea is that this is a one-tail test because we're only testing R values, correlation coefficient values less than 0. So this is one tail. We're only looking at one tail of the number line here. So that's why it's a one-tail test. So when we collected the data and again plugged the data into our formula, we got this number here. So we got negative 0.897. Okay, so now we're doing a 5% significance level test. So it's a 5% test. So now what we need to do now is we need to go to our statistics tables and we now need to find what the critical value is. So what we do now is we want to go to our tables in our stat tables that you get in the exam, and you want to find out what the critical value is. So if you just give me 1 second, my stats tables are on my desk over here. Sorry, 1 second. Let me get my tables. There we go. Right. So what we want to do is we want to go to the product moment correlation coefficient section of our stat tables. Which is what we're going to do. Well, which is what I'm trying to do right now. We're trying to find the right page. Where is it? Not this one. Here we go. Yeah, I've got it now. So what we want is we want a one-tailed 5% test. So what we're going to do is we're going to read off in your table. So I mean, let me actually do you know what I'm going to do? I'm actually going to get the Edexcel formula book up. Give me 1 second, because I want to, because when I did my A levels, I did OCR. So I actually think it's a better idea if I actually get up the real stat tables for you guys, you can actually see the real the real thing. Let me go into this here. And then I'm just going to share my screen so you can see what I'm looking at. Okay, right. So this is our math statistics tables. So we're going to go. So the section that well, okay. So this formula book that I've got here includes further maths as well. So we don't need to worry about that. But in your formula book for A-level maths, you're going to go to the statistical tables, and you're going to go to the critical values for correlation coefficient section. So it's page 37 on my document here. So yeah, let's go down to page 37. Here we go. Right, so that's not what we want. We want page 37. Don't want that. Yeah, here we go. Right, so we've got it here. So we want we've got critical values for correlation coefficients. So we want to choose with these hypothesis tests in your A-level maths statistics exams. We want to choose the product moment coefficient. So if you see this Spearman's coefficient, ignore that. We don't need to worry about that. We're just worried about the product moment correlation coefficient. So what we're going to do is we're going to, so we got a 5% significance level test. So we're going to go to the 0.05 column. So this is the level of the test. It's a one-tail test. Again, the way that this table works is that it works a one-tail test. If it was a two-tail test, you would have to divide your significance level by 2. So if it was a two-tailed 5% test, you actually want to go to the 0.025 column instead. But because we're just doing a 5% one-tail test, we just want to go to the 0.05 column. And then we're going to go down to our sample size. So if you remember from the question, let me just share the screen again back to the question sheet. So remember that our sample size from our data was 19 people. Okay, so we're going to go down on our table and we're going to read down to 19. So sample size 19, the 0.05 column. Okay, so 19 there, 0.05. Okay, right, so we get 0. I can't even read, 0.3887. Okay, right, let's write that down, 0.3887. So from the tables, just go to full screen mode, there we go. So from tables, when n was 19 and a 5% test, sorry, let me rub that out again and try and write a bit neater. When we do a 5% test, n equals 19, we got this 0.3887 value. So that's what we got, yeah, with a 5% test there. Okay, so now obviously we're dealing with negative correlation coefficients because we're looking at a one-tail test below 0. So we're looking at correlation coefficients below 0. We're looking at a negative one-tail test. So the critical value is not going to be 0.3887. The critical value is actually going to be negative 3.887. So critical value is equal to negative 3.887. And that's because, again, we're doing a one-tail test on the negative end of the number line because obviously we're dealing with negative correlations here. So what we need to do with our correlation, with our number that we got on the tables is just put a minus sign in front of it, because basically what's going on is that we got this critical, this positive critical value here is 0.38. So I've done a mistake there, 0.3887. But that's reflected on the negative side as well. So we get negative 0.3887 there. So we're just looking at the negative side of the number line. The number line of product moment correlation values. We're not worried about the positive side. So we just reflect the number over and put a minus sign in front of it because it's a negative one-tail test. Okay, so that's our critical value. So, okay, so let's think about this. So we've got, from our data, we got this number, negative 0.8, can't even remember the number now, negative 897. Okay, so 0.897. 0.897. And that's smaller than, we can see it's smaller than our critical value. So it's smaller than our critical value. So basically, if we go back to this number line that we had up here, so the negative 0.897. So this is, I mean, looking at the number here, it's very close to 1, isn't it? So it's definitely quite a strong negative correlation. And it's an even more negative correlation than the critical value correlation. So the critical values correlation coefficient was negative 0.3887. So, you know, a negative correlation, but not necessarily very strong. But what we've got here is you've got a very negative correlation because we've got a very negative correlation coefficient of negative 0.897, which is close to 1. So basically what I'm trying to say is that the data suggests we have got, the data does suggest we've got a negative correlation between X and Y. And in fact, because this correlation here, this negative 0.897 that we got from the data, because that's more negative than the critical value, it means that we need to reject H0. So our initial assumption when we did this calculation was that we assume there's no correlation, but the data is suggesting that there is a negative correlation because our correlation coefficient is more negative than the critical value. So it's a more strong negative correlation than the critical values correlation. So therefore, we're going to reject the null hypothesis. So we're going to reject H0. So therefore, there is sufficient evidence to suggest a negative correlation between the variables. So between, just write my W a little bit neat because it's not a very good W, is it? So there's a negative correlation between X and Y. So these brand new variables that we've introduced here, these X and Y variables. Okay, so that'd be part B done. So you've done part B of the question. Great. So then part C. So the equation of the line of best fit of Y onto X is this here. So use the equation of the line of best fit of Y onto X to find a model for H on M in the form H equals A times M to the power of K, where A and M are constants. So we got to use this equation here to try and derive this kind of equation here. Okay, so I'm just gonna copy out the straight line equation again. So our line of best fit equation. So it was Y equals, what was it again? It was Y equals negative 0.05x plus 1.92. So negative 0.05x plus 1.92. Now we know from the definitions that we've got in the question up here that X is log base 10 of M and Y is log base 10 of H. So we're just going to plug that in. So log base 10 of H is equal to negative 0.05 log base 10 of M, and then plus 1.9 to the end there. Okay, right. So we want to try and, as the question says, if we just read the question again, we want to try and make H the subject of the formula, basically. So we're trying to get H equals a number times M to the power of some other random number that we need to find. So what we're going to do is we've got to get rid of, we're trying to make H subject to the formula. So we need to get rid of this log base 10. What's the opposite? What's the inverse of a log base 10 function? Well, it's 10 to the power of H. So it's just the opposite of the inverse function of log base 10 of H is 10 to the power of H. So we're going to raise everything to a power of 10. So raise everything, or raise both sides, I should really say, raise everything by a power of 10. So then if we do that, we get 10 to the power of log base 10 of H, but that will just, as we'll see in a second, that will just cancel out and give us H. And then we get 10 to the power of negative 0.05 log base 10 of M plus 1.92. So as I just said, 10 to the power of something is the inverse function of log base 10 of something. So the log base 10 and the 10 in the base there just disappear. So we're left on the left-hand side with h equals this thing here. So remember our rules of indices. Remember that when we times indices, we add powers. So what I notice up here is that we got a number there, plus we got this number there, plus another number there. So actually what we can do is we can kind of like reverse engineer our laws of indices, and we can say that this is equal to 10 to the power of minus 0.05 log base 10 of m, and then times by 10 to the power of 1.92. Okay, so we've got that. Now then, again, let's think about our laws of indices. So remember from our laws of indices that if you've got a to the power of, let's just say, x times y, then that's just the same as a to the power of y all to the power of x. So again, we're kind of going to reverse our laws of indices a little bit. So what we get here is we get h equals 10. Sorry, I'll just write that 0 a bit neater again. So we get 10 to the power of log base 10 of m, and that's all to the power of minus 0.05. So what we're doing again is just kind of reverse engineering our laws of indices, and we're saying, well, we've got a number there, this negative 0.05 times by this log base 10 of m. So we just kind of put that into brackets like we've done there, and kind of reverse this law of indices that I put in the box on the left corner there. And again, we've got this times by 10 to the 1.92 over there. So I'm actually going to write it like this. We've got h equals 10 to the power of 1.92, and then times by this 10 to the power of log base 10 of m, all to the power of negative 0.05. So remember, again, we've got this like base of 10 here to the power of log base 10 of m. So again, so raising a number to a power of 10, or raising a number of a power of 10 is the inverse of log base 10. So what we actually get now is we get h equals 1.92, and then again the base of 10 and the log with base 10 cancel out because they're inverse functions. So we just get m. So you just get m, and then to the power of this number here, so to the power of minus 0.05. So everything inside the brackets there is just m, because again, 10 to the power of log base 10 just cancel out because they're inverse functions. So we just get the input into the log there, which is m. Okay, so then we get pretty much our final answer. So we get h equals 10 to the power of 1.92 times by m to the power of minus 0.05 there. Okay, so that's our formula then. So if we just read the question again, so we got, h equals a, so a number times by m to the power of k, where a and k are constants to be found. So I mean, we've done it there. I mean, you could go to the calculator to put this in the calculator if you really wanted to, but I mean, we don't have to, as long as we just say that a is equal to 10 to the power of 1.92 and k equals negative 0.05. We've answered the question. So we've got our formula for h, where a is 10 to the power of 1.92, and where k was this negative 0.05. So we've answered the question there. So that would conclude this question 6 from the stats paper in 2022. So the final question of the 2022 Edexcel stats paper. So any questions, please do leave them in the comment section, or if you want help with revision, drop me an email. You can drop me an email, and again, it's about what I charge about £1 per mark, and you can PayPal me. My PayPal is in the comment section below, so there's a link to my PayPal. But if you want help with exam questions, or if you want me to do personalized exam questions for you, where I answer questions for you and demonstrate my solutions, it's about £1 per mark is what I charge. Or if you're interested in online tutoring, maybe if you're a year 12 student wanting to get ready for next year, please do drop an email to my email, drdifferentiation@gmail.com, and we can discuss about setting up some online tutoring sessions. So thanks a lot for watching today's video, and yeah, I'll see you guys very, very soon.